All right, so we're recording this. This is class number 5. We're going to get into land air problems, and we're going to get into type 2A projectile motion. Now, a side note here, Facebook, when I went to Facebook last night, the units were gone. And someone said they turned them into guides. I don't know how that all, I don't know what's going on with Facebook. But if Facebook messes me over again, they've done it a number of times in the past where they change their format and they don't tell anybody. They don't ask me your opinion. They just decide to change something. And so that just screws me totally up. And I've had it. This will be the last straw. If Facebook does that to me, then I'm done with Facebook and I'll become the world's greatest critic of Facebook. But if it's just a minor glitch, I'm saying, okay. But if it is a problem, if we don't have units on our Facebook group, we're screwed. It's total chaos. So that was a huge deal if they just decided to just destroy it, just get rid of it for some crazy reason. I'm hoping it's a bug and it just got worked out, or they're doing an update and then now they're back to normal. I don't know.
It's apparently because they just decided to change the name, but nothing actually has changed about it.
If it's still guides, did Brandon say that or Eric? I can't tell the difference anymore.
It was Eric.
Eric, you and Brandon, you sound just the same. So thank you, Eric. Okay, I don't know why you call it guides. That's stupid. But why do you freak people out? So if it's all really the same, then I'm forgiving them. But here's why I say all this. If I make a break from Facebook, which I will one day, then I'm going to, and I had my own website, I had 2 websites on WordPress. The WordPress had its own issues. It was a pain in the butt and it was expensive. And I still have those WordPress, ASCIIphysics.org, ASCIIaphysics.com, which I still use occasionally. But I'm going to make a break and develop a website I got a couple of website guys now. And we're going to develop our own website, which is very user-friendly, and very organized. I don't care if it costs me $1,000. I'm going to put the money into it. So one way or another, we're going to get this thing organized if Facebook has decided to do this guides, which I don't know anything about that. So keep that in mind. But if you go to Facebook and it's chaos, go to this guides thing and see if that works. Okay, so let's take a look here. This is going to be of all the 10 equation sheets, this may end up being your most useful because it has the formulas up, has all the equations up there for kinematics. There's the stuff we were doing with the constants, but this is the one you'll refer to a lot with projectile motion. So today we'll be referring to this flow chart. All right, before I get going, I want to remind you that today it's really at 2:55 that the landing occurs. But if you go to the JPL YouTube channel, and Jet Propulsion Laboratory are the ones that are really just doing this in conjunction with NASA. You can watch us land on Mars. Not in real time because there's a 20-minute lag. There's two-way, just because Mars is so daggone far away. Even the speed of light still takes 20 minutes or so. So you're seeing it pretty much as live as you can get it. And Dane Sholin, and I think on the Facebook group, I put Dane in my picture standing in front of Perseverance. Now, Anthony named it, what did you name it, Anthony? Not Perseverance, but you named it something else.
I named it Fortitude.
Fortitude, which I kind of like better than Perseverance. Seems more, we're going to go out, we have fortitude. Perseverance is me more of the, anyway. So that's what they named it. Maybe the next time be Fortitude. So Anthony actually was one of the finalists in that contest. So a celebrity amongst us. So I know he's interested in watching this. I know Brandon is looking, maybe Anthony too, looking to go into astro. Jacob in another class is going into astrophysics. So they're going to aerospace kind of thing. So you really ought to watch this just for funsies, even if you're not. You ought to watch it live because you always want to know, maybe it crash lands. Ooh. But And people are criticizing it, saying, we have all these problems on Earth, and why are you going to Mars? But look, if you look at the long term, we got to get the hell off this planet. And so we need to keep making these slow moves towards establishing colonies on other planets. So I think it's necessary in the long term phase. I know people are in Austin, Texas without power. You can always say that. You can always say there's people starving in Africa, but then we can never go to space. We should never do anything but help those people that are starving in Africa. Okay, but we also got to make progress. You know, we have to. Anyway, I don't get off on that. So that's today, 2:30. Start watching 2:30. Take your mind off all this stuff around here. Now we're about to do type 2. We're about to do land-air problem. And it's going to have to do with this as a type 1 projectile motion. And in front of that, though, we're going to have the getting there part. So it's a 2-part problem. We talked about that. We did that yesterday. There's the Planet X. Okay, so now let's go to this. This is our main thing we're doing today, land air. And this is I'm going to consider this a top 10. This is a top 10. Top 10 problem. It's probably the meaning it's one of the top 10 most important problems we do all year. This is a TST as well. And I would say TST means that it's going to be on the test. So it's something worth I promise you, it'll be on the test 5A. I promise you it's worth your time looking into it. So we are recording. Yeah. So so let's get going on it. Yeah. And here we go. Make a drawing first. So you got this: the only escape from the law for Crazy Joe Clayton is to jump the river in his 57 Chevy. The river is 25 feet wide. Okay, blah, 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 blah. So let's draw it. First thing, the drawing here is really important to organize. That's your graphic organizer. So you come along here, you got a bank, you got the bottom of the river. Come up here, you got the other side. Okay, this is a profile view, obviously. And then here comes Crazy Joe. Get the colors right, orange. Crazy Joe in his car. In his car, he says he jumps in his car. So therefore, you infer from that V naught X is 0. Now, we're going to split this up into land and air. So this will be land. This part will be the land part. Land. Anything over this side, left side, is land. Because the land and the air, you'll tackle with separate sets of equations. Okay, so we have our land part, and then we're going to have, might as well draw this, we're going to have our air part. All the air stuff goes over here, which in this case will be type 1 projectile motion. Okay, so land and air. A lot of physics is just categorizing your thoughts, organizing your thoughts into, okay, I'm attacking this with this. All right. Okay, so this is land. Uh-oh. This is land. This is air. Now, the link between land and air will be this. Like a lot of times in physics, you'll attack problems with different sets of equations, and there's always links. Like a lot of times times the link, right? Times the link between X projectile motion and Y projectile motion. In this case, the link is the final velocity, the V final X on land is the same thing as the V naught in air, okay? So we call this the bridge. So you'll have on physics, you'll have a series of, I'm using these equations over here, and these equations here, and these equations here. Then I have a bridge, you know, between different ways of thinking. That happens all the time. The more complicated it gets in physics, it's just a series of you know, I'm plugging into this part of it, these sets of equations. Then I'm going to plug in these sets of equations. You know what I'm saying? And you start to become, people look at it and go, whoa. But all you were doing was you were doing sections of it linked with bridges. Okay, so here's a bridge. Now let's look and see what we have, what we're given. It says that, let's go orange here. We'll do the land part first. So it says that, yeah, nice orange color. It says that V naught is 0, but it says that acceleration, as he's heading towards the bank, he accelerates at 12 feet per second per second. You guys can stop me, Sue Zuckerberg, I agree. Maybe I should. I mean, everybody else is suing him. He's such a jerk. He's a weirdo. But you know, I kind of depend on him, unfortunately. Tied my horse to a crazy man. What else do we know? Oh, 150 feet. Delta X is 150 feet. And what else? That's all we know about the land. Then let's go and do some more work here. It says that the bank it comes off of is 5. This is not the scale, obviously, but the bank is 5 feet. So I'm going to call that, that's not delta Y, that's negative 5 feet. And then the width of the river is 25 feet. That's not delta X. A lot of students mess up right there. They call it delta X. I understand that. And then the other bank is 6 inches high. So that's, we'll keep that in terms, let's keep that in terms of feet so we don't mix up our units. Keep it in the FSS, feet, slugs, seconds. So this is 0.5 feet. Okay, anything else we're given? Of course, we know G in the air. Well, be careful because this is Crazy Joe. So G in the air is 32.2, not negative. G is positive, 32.2 feet per second squared. I think that's all. Yeah, and the question is, he's going to come along. He'll come along here in his car, and okay, come along, and then he hits the cliff at going horizontally, and then he'll go like a parabola and land on the other side. So the question is, by how much does he make it? So let's go through, now that we have that, let's go through and start buffering. Oh, okay, so let's go through and start. Let's start with the land. That's normally what you do. So you'll see this problem in tests and stuff. You'll see it on the practice problems. And usually it's like it's this, or it's, say it's Joe Dynamo running along a roof and he jumps onto the next roof, which is below him. Okay, that's a common one. It could be you, but usually something you're running, you could be running along, then jumping up, and then, you know, jumping over something. So there's all kinds of ways to do this problem. All right, so we got to find V final. Well, you tell me what equation, given what we, so you can comment here, or you can just say it. Given what we know, what equation should we use to find final velocity?
Third orange.
That was quick. True. Third orange, because we don't know anything about time on land. So we have V final squared equals V naught squared plus 2A delta X. I'm going to tell you this right now. Says we don't do enough of these problems. Every time we do a problem like this, the land will be the third orange. It's going to look a lot like this one. Maybe on top of a roof, but it'll still be the same. You know, we just don't have enough time to show you every possible scenario. So easy enough. Oh, we catch a little break here. V naught is 0. So that's not always true, but in this case it is. So V final then is scroot 2A delta X. And now plug and chug. V final then is the square root of 2 times 12 feet per second squared times 150 feet. Okay, we end up then with I'll just save you time. You punch that in, the V final is 60 feet per second. So we can box it in, I guess. So I'm going to get some partial credit on a test for knowing that much. So we're going to stick that in right, boom, right there. Okay, all the way. That's where it goes right there. Now we have our bridge. Now I know that V naught in air, and I could have done this, by the way, I did it right there, but I should have done it right here. That all goes right there for you. I had more room, so. Okay, now we do the air part. And so this will be for over here on the air part in this case, this is type 1 projectile motion. So on the air part, when you remember type 1 projectile motion, now we use the red equation and the blue equations. So in one problem, we're using orange, red, and blue. See what I mean? I mean, it gets to be a typical physics student in the fall would go, what? But now we're getting more sophisticated. So we use orange, red, and blue. So our red equation is delta x equals Vx times t. The blue equation, normally you're trying to find time. So we're going to just generically start with, and if we can change it, we will, but normally we don't. Delta y is equal to V naught y t minus 1/2 gt squared. We catch a break here, V naught is 0. And so we can solve, and look at your flow chart, you'll see where I'm going here. So delta y then equals negative 1/2 gt squared, and t. There's no reason to do this every time. You can go right to t. T equals -2 delta y over g. So back on the flow chart, we're in the yellow. Why did I make it so far away? Oh, you're kidding me. All right, we're these equations. We're doing the yellow. That's for type 1. Okay. Let me change this and move this so it's closer where I want it. Move. There you go. Over here. There. There we go. Now back to the problem. Wait, no. Okay, back to the problem. So let's plug and chug. Let's go. I always go as far as I can in the red first. So sometimes I get lucky. So delta x, what I'm trying to find, delta x then is Vx, which is 60. Now I found that out from thank you very much, from the land, 60 feet per second times time, and that's why I'm going to the blue. So the blue now we plug and chug what we know, t then equals root -2. Uh-oh, what is delta y? For 2 zoom points, what's my delta y?
-5.
I'll give you 1 point for that. So that's wrong.
-4.5.
There it is, -4.5. So -5 seems right. And they go, oh, wait a minute, the other bank is a ½ foot. So it really drops, the actual delta y is -4.5. All right, there's the 2 points. So good. You guys answer a lot faster than the morning classes. So that's -4.5 feet divided by g, which this is Crazy Joe, so it's 32.2. Probably one more sig fig than necessary, but okay. Okay, now to save time, I'm going to cheat in 0.52 seconds. So t equals 0.5. You can verify this on your own if you wish. 0. That's also important. Important. Not just to box them in, circle them, so that if I'm grading your thing, I go, oh, okay, they got that far. And like if this problem's worth 20 points, if you got that far and stopped, you ran out of time, you're going to get a 14 out of 20, maybe a 15 out of 20 right there. All right, so that time then gets plugged in right there. That's the link. So the bridge here between these two, there's also a bridge. And the bridge here is time, just t, just knowing time. Because time, x, y, time is not a vector. So it goes in both worlds. So delta X then is 60 feet times 0.52 seconds. And so you're going to get 31.2 feet, just save you time. So now if I was grading this, you get an 18 out of 20, but it didn't ask that. It asked how many feet does he make it by. Now, finally, you're going to use that 25 feet. See, if it's a student, I'll tell you, we're screwed. Students mess up on this. It's very understandable why they'd mess this up. In the projectile motion part, they automatically assume delta X is 25. Right there, you're kind of screwed. You messed yourself up. So be careful. That's why a good drawing and kind of stepping back, looking at it from 10,000 feet and go, wait, is this the lay of the land here? Don't get all stuck in the minutia of the problem. Sometimes you got to step back and look. All right, so in this case, then my final answer then is 31.2 feet minus 25 feet, and he's going to make it by 6.2 feet. And that's your final answer. You can write a sentence out. He makes it by 6.2 feet. Okay, so that was an example. It's a top 10 problem of the year. I think it's the hardest problem. If you look at it from a whole, it's the hardest problem so far. We're going to the one on the end of the sheet will be the real hardest problem so far. But that is the top 10 important problem of the year. First one, I think. We got 9 more that are harder than this that we'll get to this semester. Unfortunately, physics doesn't get easier. I mean, maybe it gets easier because you start realizing, okay, this is how you solve a problem. But anyway, now we're going to do the last thing we're going to do here. Still got 10 minutes or so. Actually, I have till 2, technically. So I got 20 minutes. I can take my time. Don't need to rush. Your homework is, I feel like I was rushing this morning. Oh, as usual. So the homework is 2 and 3. But we're going to do a lot of 2. Okay. We'll do the first half of 2 together. So I think we started talking about this because yesterday, only in this class did we start talking about it. Right here. Yesterday, we started talking about that, right? We said it wasn't this picture, but it was a similar idea. This is type 2A projectile motion. And so the yellow arrow, just to remind you, the yellow arrow is Newton's first law arrow, meaning that a body in motion stays in motion. So this body, whatever it is, a long jumper in number 2 or a baseball, whatever it is, should keep going like an arrow forever and ever and ever, instead, unless acted upon by an unbalanced force, and it is. In this case, gravity is acting on it. Nothing's, assuming air drag is minimal, nothing's really acting on it x-wise, but in the y direction, you have that unbalanced pull back to Earth. And I call that like an Earth tax. It is a tax that's put onto that ball that's flying through the air. And it starts off really, it's very patient. That tax starts off really small. Here it is. It's a very small little tax. Barely notice it. But then as it grows, say every quarter second or whatever your time interval is, that gets angry. And it gets bigger and bigger exponentially. And the reason is it's that orange arrow comes from the tax from the Earth. The yellow arrow comes from Newton's first law. Oops, that's the yellow arrow part. Just for right here. So yeah, so like the moon does not offer near the tax, does not require near the tax that the Earth does. The Earth is requiring 981 centimeters per second every second. That's like highway robbery. The moon is only charging you 167 centimeters per second every second. That planet X we looked at yesterday, that only charged you 25 centimeters per second every. That was a deal. You can go a long way on that planet, quote planet. It wouldn't be a planet, you know why? That from yesterday, it wouldn't be a planet because planets have to have their own. They have to have enough gravity to have their own atmosphere. That's why Pluto got kicked out, folks. It wasn't anything personal. It's just that Neil deGrasse Tyson is not to blame, but they got together as a committee and said, you know, Pluto doesn't really have an atmosphere. Although we love the name and it's cute and all that, it's not really a planet. It's a dwarf planet at best. We should send Zuckerberg to Pluto. He can suck it. Okay. Sorry, Zuckerberg, if you're watching this. Just kidding. Okay, here we go. Not really. Here we go. So here's this one. Here's the situation. Got a drawing here. They're jumping at 20 degrees. So I got my initial arrow. Now we have an angle. And then it's going to have this purple path. I make it purple because purple is kind of a combination of blue and red. I don't know if that's true, but I just made it up. So purple is a combination. Everybody knows that. All right, so it's a purple path. Now, we need to concentrate, though. This is type 2A. We need to concentrate on what's going on to begin with. So we talked about this yesterday in here. It's the only class we talked about this in. But we have it doesn't hurt to repeat it. This arrow has a Y component. Did I ever tell you guys that an arrow at an angle is the hypotenuse of a right triangle? And then this is the orange part. No. The red part. That's red equations. No air drag. So that's the red part of the initial velocity. So this is the arrow V naught. That's the vector. And that's equal to 9 meters per second. And then we have theta here, and that's 20 degrees. And so, but really you can't, at no point in your problem, unless you're doing head to tail method, will you use 9, just 9 by itself. You'll always need a component of that because computers, humans, whenever we're doing equations, you can't, as far as I know, you cannot do a set of equations when you're mixing up X's and Y's, unless it's head or tail, because computers can't do arrows. Computers can just break them up into matrices. They break them up into X, Y's, and Z's, but then they attack them one at a time. Okay, so anyway, so this is V naught Y. This is Vx, and yesterday we said this. Why call it? Why you don't need to call it V naught because it doesn't ever change. And so V naught Y then is going to be V naught times sine theta, and that'll always be true in this class. And then it'll be sine because it'll be the angle be from the horizontal in this class. I'll make you that promise. Now your professor maybe not make you that promise. This is V naught cosine theta. Okay, so let's plug in some numbers here. Our numbers then would be 9 sine of 20 degrees, and that is all meters per second. And that ends up being 3.1, to save your time. Make sure you're in degrees. 3.1 meters per second. Someone can check me on that. To 2 siggies, I believe that's right. And down here, thank you. Down here we have 9 cosine 20, and that is 8.4 or 8.5. Yeah, it's one of those.
8.4.
Okay, so it's 2 siggies. I said 8.5. I said 8.45 in third hour, and Roman said, no, it's too many siggies. He got two Zoom points for that one. He caught me. Yeah, you can't like in the problem if he gives you 2, you can't go 3. And then someone else called me on this and said, wait a minute, why is that 20? Why isn't it 20 point? Because 20 is 1 siggy, 20 points 2. You're right. We'll fix it this summer. Okay, so that's what we know so far. Haven't even started the daggone problem, but that's a big part of it. So it says, the first question says is how many meters does he jump? So I want to know my red delta X. It's red, it's not orange. So my red delta x, question mark. Okay, now it's projectile motion. So we go as far as we can in the x. We say delta x equals Vx times t. And so delta x equals, well, we already know it's 8.5 meters per second times t, but I don't know t. So I got to go to the y. But I can't do what I did up here. This is one of the number one mistakes students make, is they plug that in for time so they're using the wrong set of equations for the wrong situation. Physics, that's where physics gets hard, because it's all about synthesis, being able to look at situations and apply the right set of equations to that situation. That's why you have equation sheets, which in the hand of somebody who doesn't know what they're doing, just all it's going to do is cause them confusion, and they're going to put the wrong equation where they shouldn't. So you got to say, no, this is not type 1. This is type 2A. So there is an equation there in the flow chart. Let me show you where that came from. So let's go with our delta y, blue. Delta y equals V naught y, which is V naught sine theta now, times t minus 1/2 gt squared. So no longer can we make V naught y 0, but we do catch a break because delta y is 0. Ultimately, it's 0, right? The long jumper he's not jumping up onto a ledge. He's not jumping off a cliff. He's jumping and then landing at the same elevation he took off at. So there is ultimately no delta y. So we get a break there. So now if I say 0 equals V naught sine theta t minus 1/2 gt squared. Now, and I'm going to make that t times t instead of saying t squared. You'll see why. That's really t times t. But notice, can't I divide both sides by t? As long as t isn't 0, and you assume it did take him time to jump, so t is not 0. Don't have to worry about that. So that goes away, and that goes away. And now I'm left with, and then I can do it this way. I can then say that V naught sine theta is equal to 1/2 gt. See, convince yourself that's right. If they subtract to equal 0, they must be equal to each other. And so finally, we have a new equation for time. The equation for time for type 2A anyway is this one. Boom. Erase that. Let's erase some of that. Give me some room here. Don't you wish you could do this? Get an iPad and you can. Hey. All right, so we go t then equals 2 V naught sine theta all over g. And that is the equation. If you look back now at the if you look at the flow chart, that's the equation there that you use to find time. Okay, for type 2A. Very specific. So now I may leave it all up to you, but let's see. Now you take that, that's as far as any other class got. You take that and you plug that in for time. You plug in your numbers. I'm kind of doing your homework for you, so I don't want to do too much more. You plug in your numbers and you find out what time it is, and then you find your delta x that way. And just check the back of the page, see if you're right. Okay, make sure you're using the right G, which in this case is 9.81. Make sure you're in degrees, not radians. Now before we do it though, let's take a look at the maximum before you do it on homework. It says, what's the maximum height that he jumped? So we're not gonna work this one, but you tell me, what are you gonna do? How are you gonna work that problem? Two ways to do it. One dangerous, one safe. How are you gonna do it?
Could you use half tau?
Boom, and that is the dangerous way to do it, but that works just fine. So dangerous way, I'll tell you why it's dangerous in a minute, but dangerous, but still working, dangerous. Use half tau. I like the way you said it. Use half tau, okay? That works for type 2A, does not work for type 2B. The reason why it's dangerous is students try to do it when it's type 2B and you can't. The safe method, anybody want to venture a guess on the safe method?
One of the blue equations, maybe?
Yeah, it's the third blue. Third blue is a safe method. Now, what will the velocity in the y direction be at the apex? Once it reaches
0.
0, and there you go. And that's true for blue, for type 2A or type 2B. At the apex, we know that V apex in blue is equal to 0. That's blue. Not red, it's still chugging along. It's on the conveyor belt. But in blue, that's temporarily 0. So the safe method is use third blue and set V final, which is at the apex. I'll better say V final parentheses apex. I better not say V final. I better just say V apex. V apex equal to 0. It's kind of like the second, not really. No. Set V apex equals 0. So in that case, you would say 0 equals V naught sine theta squared. V finals. Wait, V finals V naught squared. Okay, that's that. Minus 2G delta Y, and then solve for delta Y. So in that case, your apex height will always be, this is true for type 2A and 2B, apex height will always equal delta Y, which would be V naught sine theta, V naught sine theta, parentheses squared.
Couldn't we just use the first green since V apex equals 0?
You could if you're given tau. If you have to know tau for first green. So then once again, you're cutting time in half and you're in that same problem. You got that same issue that will arise. This is all over 2G. This by far is the safest way to do it, to find apex height for a projectile motion problem. Right there. I don't have that equation in the flow chart. It's kind of a pretty specific case, but okay. All right, stop sharing. Okay, so there's your work for today. Tonight is 2 and 3. Don't do 4 yet. Don't do 4. I'm going to show. Well, 5 will show us the derivation of the range equation, which is probably the most dangerous equation we do all year. But it's such a great shortcut. You just can't help yourself. I'll go ahead and teach it to you because someone's going to teach it to you. But it does come along with its own. Every shortcut comes with dangers. All right, because you're always assuming things. With shortcuts, you assume things, and assuming stuff in physics will get you killed. Like I assumed that opening up all the spigots and turning it open and that was going to save me, and it was not. I didn't know about that pipe. I did not even know that pipe existed. I was shocked. Anyway, so when it burst. So, okay, maybe I'll stop the recording, huh?